Hello, I think we're recording. Welcome to this third video in a mini-series of 3 videos in total, where we're building some laser cooling thing. It's a simulation. So obviously, if you haven't seen the previous 2 videos, this will make a lot more sense if you start from the first video. So anyway, all we've got to do in this final video is make these atoms look more like atoms. So I definitely want some electrons orbiting around them. So I think I'm going to create a new object, an electron object, and then each atom will be able to, when it's instantiated, when each atom is created, like I'm doing now, by tapping on the screen, it will also, in its own constructor, instantiate a few electrons, perhaps a random number of them, something like that might look better. And I've got to stop these guys going out of the screen as well. Off the canvas. So perhaps what we could do is add a force when they approach the boundaries of the canvas. We'll add a force, so some acceleration to them. Let's do that to begin with. Let's try and do that. So I think that's a behavior that belongs to the atom. So it's best that we make this inside the atom object itself. So here we are. Jiggle is a function, render is a function. That's the end of the constructor of our atom object. So let's just make a new function here, and we'll call it bounds, for like boundaries. And I'll just put some comments in here, like a good little programmer, so I know what I'm doing when I look back at this in 9 months' time. What do I want to write? What does it do? Okay, so when atom approaches boundaries of canvas, add a little force to kind of push towards center again. There we go, nice and simple. Okay, so we need to ask a question. If this atom's position, and let's deal with the x-axis first. If its position, let's say, is less than 0 plus, and let's say this atom's radius, that'll do, then we want to push it that way. No, we don't. The way you're looking at me, we want to push it that way. So we want to say this acceleration x plus equals, now we want to decide on a force. This wants to be like a boundary force, so BF will be our boundary force. So we better go and define that here. Boundary force, and that's going to be 0.1. I'll try 0.1 to begin with. I might actually have to write BF though, and let. There we go. Right. So that won't be working yet. These atoms will still be able to jiggle their way off the screen, because this bounds function isn't being called yet. So it makes sense to call it every time we update the atom's physics. So this function, if you remember from, I think from the first video, is where we're adding the acceleration, so that's forces, to the velocity of the atom, and then we're adding the velocity to the position of the atom, and then we're cancelling out all the forces, waiting for the next frame to add on the forces as we want. And we're using this, just a reminder, we're using this .add function because .vel and .pos and .ac are all vectors. They're holding, for us, 2 component numbers. It's x number and y number, which correspond to the movements and momentums and things on the x and y axis. Anyway, so before we apply all the physics, we do all the physics, we want to go and call bounds. So you have to write this dot bounds so that we know that the function is a member, or it's a member function of this object. Okay. Stop atoms wandering off. That gets the idea across, I think. Doing very good comments here. We're doing very well. Okay, now, because I've written that, it should... Oh, there we go. As we put an atom too close to that boundary, a little force pushes it back towards the middle. So it's working. And it's very pleasing to see, because you actually see the acceleration, the application of the force. It's perhaps a little bit strong. So let's change his bounds. Let's change that to, I don't know, is by a reduction of a factor of 10. That's perhaps not strong enough. Just halve it. Okay, that'll do. I'm sure that will do. Right. So now we can do lots of copy and pasting, and we want to do this for over here. I want to do it for, yes, this area there. So we want to say if x is greater than width, which is the P5 keyword for the measurement of the width of the canvas, minus the radius of the atom. That's kind of bugging me. The radii of our atoms isn't really this, because the radius, the way I'm drawing the atoms, is twice that, so it's really diameter. Anyway, now I've said it, at least we all know it. At least we all know our dirty little secret. Anyway, we want to, if we're hitting the edge of our canvas, we want to go minus on the x-axis. So now, yes, our atoms are kind of penned in terms of the x-axis. So all we have to do now is copy and paste those two, and be careful in changing for the y-axis. So first I'm just going to change every x I see to a y, and then we need to figure this out. So if y position, so that's up here, is less than 0 plus rad, then this ac y acceleration plus that. Oh, that's worked fine. So we've done that. If our position is greater than the width, we need to change that to height, minus, yep, the radius, then acceleration minus equals. Okay, so now we should have boundaries on all four sides of our canvas. Brilliant. So our atoms can they can cross those boundary lines, and actually it gives them a little bit of I don't know, more momentum than they should have. They're picking up velocity. We won't worry about that. Enough of them are staying on screen now, so I don't know, I'm kind of happy with that. That's enough. Really, this is about the laser cooling, which we got working in the second video. And the last thing I did was create this Boolean variable, let zap on equals false. So if I change that to true, that will switch on the lasers from the off. And as you can see, the atom is jiggling a little bit, but the laser system, to simulate what this can happen in real life, scientists have now done, to simulate cooling, say, a gas. I think they use, was it sodium, I don't know, a sodium gas or something, cooling it to something very, 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 very close to absolute zero, so 0 Kelvin. Look at that. Right, one thing I didn't do on camera is I've written this text up here, tap to add atoms. I'll just show you how I've done that in the draw loop, because it's something drawn to the screen. There we are. Nota bene, these lines not in tut video. So to choose the fill color for our writing, you write fill, just like when we're drawing the spheres, the circles, sorry, spheres, or rectangles and things, or lines. No, lines, sorry, lines, the color of a line, you use the stroke function. For a shape, use fill for the inside. Text, so this function works like this. In quotes, the text that you want, the message that you want to print to the screen, and then the last two arguments relate to the x and the y dimensions of your screen. Actually, I've kind of hard-coded those numbers. It would be better to do something like width divided by 20, and then I don't know, height divided by 20. So that means whatever dimensions of browser window that your user is using, those numbers will be kind of dynamically related to that in the first instance. Not really dynamic, but that would be better. Also, we could change the size of the font. We do that with the p5 function text size, and then in here you simply put a number. I think this is where actually we want to relate this maybe to the height of the canvas. Divide that by 20. That's quite good. That's quite a nice size. And then you know what? Let's just create a variable. Let text size equal height divided by 20. And then use the variable in here, and now we can use it in here. TS capital S and TS. Yeah, that's kind of nice. Maybe times 2 or times 1.5. Yeah, that pleases me. That's that's okay. Okay. So if we have a very small window and things like that, the text will kind of shrink. If we had a large window, the text will get slightly bigger, which is a better way to code things, I think, to be aware of that in this modern age. Right. Okay. So we've got our boundaries. So that means more of our atoms are staying on screen. I think we've just got one more thing. Oh, we've got to be able to turn on the laser, turn it on and off. So if we go to mouse pressed, at the moment we're creating an atom every time we press the mouse. So really that doesn't belong in mouse pressed. We should call that function explicitly. So we should have a function called create atom. Let's put that text, that code in there. And now we can say create atom. So that's a bit tidier. So it does exactly the same thing, but in a more appropriate way. So now in here we've got space to ask the question. So if we made a little button, we'll just draw a rectangle. Top right perhaps? Would that look good? No, bottom right, I think. So let's say, actually we've got to draw this. Let's draw it last so that it appears over everything else. Okay. Again, I'll say draw button. Create a function call. Much better practice. Function draw button. Then we want to say rect. So that's the p5 function for draw rectangle, and we want to go from it. We draw rectangles from the top left corner to the bottom. That's how you kind of imagine it in your mind. So we want to say something like width minus, I don't know. Again, we should create like a little variable, and we'll call it button BS for button size equals the width of our window divided by, I keep using 20, well let's use 42, keep Douglas Adams happy. So there we can say width minus button size, I think. So that's the X location. Height minus button size, let's say. And then we need the dimensions of the button itself. BS, and then BS times golden ratio 0.618. I can see our button down there. I don't know if it's because my window is so small. That's quite small. So let's, sorry Douglas, let's say 12. Yeah, we've got a button down the bottom. It's not quite where I'm expecting it to be. Oh, that's the top left corner. Right, I've gone too high. Oh yes, minus button size. Sorry, on the Y dimension, we've got to times everything by 0.618. So that we create a little rectangle that has the golden ratio dimensions. Apparently, this is the kind of dimensions or ratio that's most pleasing to the eye. I think bank cards and things are that ratio or something. Okay, but that means now that we can just change this number. That's going to be huge. Yeah. 8, and the ratio of our button will stay the same. That's kind of cool. We definitely need it to be red, I think. So fill 202 or 222. No green, no blue. That's good. And stroke weight. Let's reduce that. It looks a bit too silly at the moment. 2. That's nice. And maybe stroke color. Don't like the black. Maybe white. So 255. Yeah, that looks better. So what we want to happen now, we've affected our text. It's kind of nice like that though, our text. Okay, I'll leave the text like that. The text, by the way, I haven't changed the stroke or the fill, I don't think, the color. So this is affecting the stroke and fill color of the text as well. Something to keep in mind while that's happening. So I want to keep in mind the dimensions, the location of our button. Let's make this a global variable, BS. I think I've used that for something else. So I'll call it BUS for button size. BUS. So I think we're going to need this variable for actually detecting when we press the mouse or tap the screen to press the button. So let's put that here instead and say, oh, this won't work, you know, button size, because width is null at the moment. We only get width to be, we can only use width as a keyword after we've created a canvas, because that generates what width means. So quite an easy fix. We'll copy that, just leave bus up there, and here we can define what our button size will be. Okay, so now we can use BUS. So back in mouse pressed, this should be the final step for getting our button to work. So all we essentially have to do is say, if we press the button, then zap on equals not zap on. So the opposite of whatever zap on is. If it's off, turn it on. If it's on, turn it off. Nice efficient line, that. Okay, for dealing with Boolean like toggle things. Okay, so actually this might work already. You look, yes, we can now toggle our lasers off and on, but it doesn't matter where we click. What we want to do is ask a question first. Have we tapped over the area where we've drawn that rectangle? So you want to say if mouse x is greater than, see if I can remember this, greater than width minus button size, is that right? It's greater than that. And mouse y is greater than height. Oh, I think I know what the answer is. Height minus the button size, but the button size times 0.618. So now, yes, it's beginning to work, I think. We can create atoms over the canvas anywhere we like, but if we click, very close to the button, if we click the button itself, brilliant. We can toggle, and only there we toggle the lasers on and off. So we've created a button. We need to just add something here. We don't want to create an atom if we're pressing the button, so we could just turn this into an else create an atom. So there we go. Now the button just serves as a button to turn on the laser, or the lasers, yeah, and nothing else. Brilliant. So this is kind of functioning much more as we wanted it to function in terms of the laser cooling. Right, talking of quantum stuff, let's go and create some electrons. So right down the bottom, so that's the end of the atom object. We want to create a new class, and I'm going to call it Electron, and we need a constructor. I imagine it'll have an X and a Y location. Right, so we're going to say this X equals this position equals, you know what, we might be able to copy most of what we've done in our atom object. We probably just want a position, and we're just going to, you know what, we're gonna just need a position, and I think an angle, I'll call that theta, equals 0 at the moment. So so that would be kind of the orbital angle. How much has it orbited around our atom? Because I'm thinking every time we make an atom, it will generate a load of little electrons, and they'll keep track of their own like angle around their like parent atom. I think that makes sense. Yeah. And then in each update of each atom, we just need to increase theta, so the angle, and then use polar coordinates to rotate those electrons around the parent atom. Okay. That sounded simple. We should be able to do it. Yeah, let's just try and draw some electrons first, and then we'll try and rotate them. So we'll call this render, and then we want to we'll just say stroke white, because that will be opposite to the outside of the atom to kind of contrast them. That might look good. Maybe I need a kind of uniform style though. Maybe if you have black outlines somewhere, you should have them everywhere. I don't know. We'll see how they look. And then the fill color definitely needs to be blue. So no red, no green, but quite a lot of blue. Let's go 222 again. And finally, they're going to be little circles, I guess. So ellipse, and it wants to be this pos dot x, this pos dot y, and now the size. this radius. Okay. So we need to add a radius, this rad. Equals, how big were our atoms? 42, weren't they? Were they 42? Yeah, radius is 42. So maybe these need to be really small. I don't know, about 4? 4 sounds nice. Okay. So our atom how are we going to relate the two? So in the constructor of our atom, we want to now instantiate my electrons. Smiley face. So maybe we need to create an array of electrons. So this dot, I'll call them elects, equals that. And let's just make one to get it going. So this dot elects push, so that's pushing an object onto this array, and we need to create a new electron, and it's going to be created at this atom's location. This dot pos dot x, this dot pos dot y. Okay, so really that position, we need to think about it as the origin, the center of origin of the rotation of the electron. Okay, and that needs to be updated. So every time we move our atom, we need to then say this dot update electrons, and let's just write ourselves a little function, update electrons. So that's going to update positions of array of electrons. That's what that's going to do. So we're going to say we need like a for loop. So for I equals 0, I plus plus, no, I is less than this dot elects dot length. I don't like how this is formatting. Can I just make that a little bit, make our canvas, our browser like canvasy window a little bit bigger, smaller, so that our code window is a bit bigger. I plus plus. Right, that's our for loop. What have I done wrong there? Something's bad there. Do I have to write let I? No. No. Oh. Okay, sorry. Got confused there with the formatting and things like that. Okay, So this for loop will cycle over all of the atoms that we've got in our array. This is definitely crap. I've done something wrong here. Do I have to write let here? Yes, I do. Sorry, I've forgotten how to write a simple for loop. That's what basically was going on there. Let me just have a look at another for loop. I can't believe this. I've just confused myself. If I go to the draw loop of our main program, yeah, let, and there's no semicolon there. Anyway, right, electrons, no, back in our atom. Okay, so we're cycling over our electrons. And we're going to say, oh god, this dot elects I. So that electron, first thing we want to do is update its angle. So theta plus equals, I don't know, 1. Then we need to find its new x and y position using polar coordinates. Polar coordinates is just finding an x and y location relative to an origin point, xy, and a given angle. And x and y will just change like this using cosine and sine. So we want to say this dot elects I dot pos dot x equals our origin point, which is origin point needs to stay the same. Okay, so we'll pretend we've got an origin point. Xi. Oh, our origin point will be the center of the atom. This is more efficient. Okay, so I can just say this dot pos dot x. That is the center of the atom, because update electrons is a function, is a member variable, a member function of the atom object. So I can just say this atom's position x. Plus, I think I say, plus the radius. So this is the distance away from the center of the atom. Let's just say this dot rad, to see what happens there. Times, let's put this on one line, times math dot, what is it, lowercase math? I think it's uppercase math. Math dot, now x is it cosine or sine? I think it's sine. It's probably cosine. Sine theta. Okay, so that's found the x position, and theta, every time this is updated, will go round, round, round. So now we just need to copy that, change sine to cosine, and I might have to update that. Change that, and then write this in terms of y. Okay, right, so we're updating the electrons, and we're going to cycle through all the electrons. At the moment we're just creating one, and we're creating that in the constructor of our atom. Here we are. So we create an array of electrons, and we just push one electron, and we say its position is the origin. We could just say 0, 0, because the update loop is going to, so the update function is going to change theta and find the polar coordinate of the electron. So now the final thing we need to do is render our electrons. So I think we're already cycling through our electrons in the update, so we might as well render them as well. Why not? So after we've done that, let's this elects, so we need to get the individual electron and then render it. So we're using the electrons render function. Okay, and that is not working. I cannot see. I can't see an electron appearing. So the problem is almost certainly within all this. But let's just go through the steps that the computer is going through. So we create an atom. We create an array of electrons. We push an electron onto that array. Let's just see if everything's good so far. Ellipse, this, positive, rad. Maybe let's just draw it quite large. Nope, I'm definitely not seeing any electrons. Theta 0. Go back to 4. We are rendering it, okay. Red, green, blue. Oh, do we have to give it... No. So it's not how we're rendering the electron. Problem must be here. Oh, length plus 1. No. If I is less than length, the length is 0. No, the length is 1. We start from 1. No. Let's try updating our angle a lot slower, just in case it's whizzing around and that's why we can't see it. That's not the problem. So it's probably in here. Our position equals... We have got a position, haven't we, for our electron? This xy, this pos equals create vector x, y. It's got theta, it's got radius. Oh, what is it? We are drawing the electron, aren't we? In the right place? That's still within the... Yep. And it is called render to draw our electron. Yep. This pos is... Have I written ellipse correctly? Let's just compare it to the render function. Ellipse stroke weight 4. Pos y, pos x, this rad. Yep. Stroke 255. Yep. I think we're drawing it right. Okay. It must be in here. The problem, the bug. This elects I, the pos x equals pos x plus this elects pos y equals position of an atom plus this radius times math cos. Is that sine? Is that cosine? Oh no, this is so frustrating. This theta. Maybe theta has to be radians. I think I can just write radians. Sorry, radians. And P5 will convert this number to radians. That wasn't a problem. So I should probably return this to what I instinctively thought. Update electrons. Let's try it here. No, it doesn't matter where we're calling that. Let's try just drawing our electrons without doing the polar coordinates. See if we can home in on what's going on. Ah, electrons being drawn up there. So electrons being drawn, so our kind of white coloured though. Let's just change the stroke weight. Stroke weight 1. Yeah, so it kind of looks blue now. So we are drawing electrons. So something I'm doing in here is wrong. What am I doing wrong? Oh, theta. That belongs to the electron. Oh, I can only imagine that you saw that very early on and you were screaming at the screen, and I'm sorry. This dot elects. There we go. Right, we've got electrons. Beautiful. And they are rotating. They're kind of going anti-clockwise. I guess I'll leave that like that. We definitely want to increase that, so make them go 10 times as fast. Yes, now we can see them circling around our atom. That's really cool. I think they can move a little bit faster. Maybe 3 times as fast. Maybe we'll call it 3. I think I can just write pi. Yeah, there we go. So they move at pi. They need to be a little bit bigger. I've got them at 4 at the moment. Let's call it 8, twice as big. That's kind of cool. And we need to give several of them to the atom. So where is our atom constructor? So at the moment we are just pushing one new atom. So we want to say let number of atoms equal math random which math.random just gives us a number between 0 and 1, a floating number. So you can scale it up to, let's say, 3. And then we want that whole thing to be floored or something. Oh, that can be 0, will it? Plus 1. What have I written there? Math random times 3. That's fine. Let NA. Does that have to be a capital? No. What's going on? Oh. No. Does that have to be a capital? Nope. Let NA. Oh! I'm writing in the middle of a badly formatted line. There we go. Right. I want to do it here. Okay, so all of that was kind of okay probably before, except for random. Yep. So math.floor just rounds down basically, so that we get a whole number. Because I want a whole number here. Number of atoms has to be a whole number because I'm going to use it in a for loop. So I'm going to say for I, let I equal 0. I, well, I is less than NA and I plus plus, and then I want to push a new electron onto here, but I want its theta to be slightly different. And you know what? Let's add a third parameter for when we construct our electron, and we'll say that's theta. So we'll say let's just say I times pi, which is great, some kind of like a random number or something, or not a random number at all. So now in our electron constructor, oh god, where is it? Near the bottom of here. Yes, we need a third variable, a third parameter t, and theta will be t. Okay, so we're seeing new more than one atom be created, but I've not spread them out enough because I don't know what I'm doing. So instead of that, let's I times Douglas Adams. Oh, that's working better. Yeah, lovely. Actually, much more than Douglas Adams. How's that? That's a little bit better. So we get them at certain intervals and things. Oh, they shouldn't be in the same energy levels. Oh god, we need to... Atoms wouldn't look like that. Electrons would have different orbital radii. I'm going to let you figure that out. Anyway, we could create a different number of them. Where are we? So times, I don't know, they can have as many as 7, something like that. Oh, that looks really cool. We can have as many as 7. We can switch on the laser to cool them down. They don't really look like atoms, but there you go. And I think that's it. I was going to do something else, but I can't remember what it is. Okay, so this video has gone on for way too long. I'm really sorry about that big chunk of debugging there. I'll keep it in because I don't do any editing. I haven't got the time for it. So there you go. Thanks very much for watching this mini-series. There you go. I'll put the link to this CodePen in here, and you can improve the look of this because it's disgusting, and you can make the atoms look more like atoms. Thank you very much. Thanks for watching. See you next time.